Okay, so the recording started. Yeah, recording started. Okay, so this week we are going to, not surprisingly, move on with the next chapter because we're doing things in order. And the next chapter is threads. So this is kind of a continuation of our discussion on processes last week. But threads are slightly different. When we create a new process, you'll remember last week we talked about a process control block. So a new process has a new ID, it has a new section of memory, it's a new set of registers, a stack, a heap, all that kind of stuff. A thread is a more lightweight thing. It's a smaller kind of process that shares the same code base, that shares the same memory base as the underlying process, but does get some new data to use. So a new stack or a new heap to have some data that it can store. The idea is that with a lot of processes, you'll be doing a lot of sub-processes, which might be quite simple things. So for example, you might have an image that you want to edit and you add a filter, and that filter is going to brighten every pixel by 20%. So you have to go through the whole image, taking each pixel, calculating the new brightness and saving it. Well, for some images, that's quite a lot of pixels, so you could do it one after the other. Or you could make use of the idea that quite often we can work in parallel. So if we have multiple cores, we can do 2 pixels or 4 pixels or 8 pixels all at once. So the underlying process will send out a whole bunch of threads that says, we'll quickly perform this operation on this bit of data. So the process owns the data, which is the image, and it tells the thread, yeah, go and work on this very specific part of this data. So threads tend to be very lightweight. They're not massive bits of code. They tend to be small things that can be carried out, finished, and then sent back to the main process. So small things that we can do in parallel. So image manipulation, looking at network traffic or I/O queries in general. These are all things that we can send out to threads. So, as with other things, different operating systems have similar ideas, but implement them in different ways. So let's think about what it is that we're going to do, what options we might need to have, and then we can maybe look at how some different operating systems implement that. So, as I say, all your threads run within the application, and you can have multiple ones connected to that process. A check on a game controller to see if you've pressed a button, a check on a menu, an update for a display, show a poll graph, a background process to check the word that you've just entered into your word processor, so it knows whether you got it, whether you spelled it correctly or not. Lots of small things that can run away on their own. And if, while you're typing in your word processor, you're 3 words on when that thread returns to tell you the words spelled correctly or incorrectly, that's fine. You can just update it then. So, small things that don't take a lot of time or resources to create, like processes do. We can use threads for those. And kernels, so the internal part of the operating system, the most protected part, can generally run lots of threads at once. They are multi-threaded. So by setting up these threads, these lightweight threads, we can get more work done, which is quite often what we're trying to do. We're trying to make the best use of the resources that we have, whether that's CPU or memory or storage or networks or whatever it happens to be, and threads help us do that. So we tend to set them up in this kind of way. We just have a thread server and we'll set up new ones as we need them. The idea being, because they're small, they respond quickly. They're not reliant on other things. So if your word processor is busy printing something in the background, that's okay. The thread that's checking the spelling is still running away. We don't have to create a big heavy process with all of its data. We don't have to copy over the document that we are using to this new spell check process, because it makes use of the data that it already has in memory. So it shares all those resources. So it's a lot faster, a lot better to use. And if we have multiple processors or multiple cores or both, then threads are easily able to take advantage of that. So like I said, with the image one, if we suddenly find we have 2 cores, we can do 2 pixels at once. And if we find we have 4 cores, we can do 4 pixels. So we can make use of all of the resources that we have, whether it's a multi-core or a multi-process CPU that we have. And of course, that's a big issue in terms of creating systems. Not everything is suitable for multi-processing. So you might think to yourself, okay, well, if we have multiple cores or multiple processes and we have a spreadsheet, and at the bottom of the spreadsheet is a sum, well, why don't we just send all of those columns to different processes and get them to add up? Well, that's fine as far as it goes, but what if the number in the second column relies on the summation of the numbers in the first column? In other words, there's a relationship there. You can't work out column 2 until you've worked out column 1. And if you do work out column 2 before working out column 1, you get the wrong answer. So it becomes difficult to understand the dependencies within any non-trivial system. And if we try and set that up, it becomes really difficult for the programmer to do that, to be really clear about what bits depend on each other and which bits are on their own. Using multi-programming at that very small level to do tiny things means that we have less of a problem in that sense. We don't have to worry so much about the dependencies because we're not adding up a big pile of numbers. We're just calculating one number. We are manipulating one pixel. We are checking one I/O device. So it's very discrete things that we can say, yeah, we are fairly safe that if we do this, we can do more than one at a time and it won't affect anything else. So when we are programming these things and when we're implementing them on an operating system, having an operating system that implements threads can help us get our systems working faster. Because there's another twist to the tale. Because what I've been talking about is data parallelism. I've been talking about things where we are working on multiple pieces of data at once. We take the data, we split it up, we assign it to a different task, a different thread, and it gives us a result back. We don't always have to do that. It might not just be data parallelism, it could be task parallelism. So we could do multiple tasks at once. So one thread could be doing the spell check, one thread could be updating the style, one thread could be checking to see if your shared document has been changed anywhere else. So you're doing multiple tasks at once as well. So parallelism can either be about tasks or it can be about data, depending on what you want to do. And as I say, unless you have that set up in the operating system, that becomes really hard to manage. So it has to be built into the operating system at its lowest levels. So we end up with something like this. So originally we've been talking about, when we talked about processes last week, we spoke about a process being given the CPU for a certain amount of time. So a task gets it, and then the next task gets it, and then the next task, and then the next task, and then it goes back to the beginning, and so on. If we have multiple cores, then we can do multiple tasks. We can run task 1 and task 2. And we can expand that out, as well as having a single thread of execution. We can have multiple threads of execution, carrying out multiple lines of code at the same time. Now you'll see here that normally with a single threaded process, one thread of execution, we have one process with code, data, files, registers, stacks, all that kind of stuff that's needed to support the program, and then one thread of code execution. What we do with multiple threading is the code, the data, and the files stay the same. So we're using the same code, we're using the same data, we're keeping the same files open. All those big, heavy, resource-heavy things stay the same. What changes is if we set up multiple threads of code to run, we can give them their own set of registers to store some data and their own stacks to store more data. The difference being registers are faster than a stack. So registers are data storage on the CPU, remember? So they're close to the CPU really fast. A stack might be on the CPU, but it's more likely to be on supporting memory. Still fast, but not as fast as registers. Either way, we share the same code, share the same data, we share the same files, but we give each thread of execution its own set of registers and its own stack so that it can store the data for its own process. So thread 1 might have a register that stores the value of the pixel in location 1, second thread might have the value in location 2, and so on. So the file is still there, thread.jpg, that's still been loaded into memory as data as thread.jpg, but that might then be distributed to each thread by taking each part and putting it into a register. And any manipulations that it has to do as part of that code, it's got its own stack to work. Okay, does that make sense before we move on? Anybody get any questions about that so far? Okay, so if we're talking about running multiple threads, we're talking about doing more than one thing at once, we should probably try and work out how much adding in this extra hardware helps us, because it's not free, clearly. If we put in another processor, there's a cost. The cost of the processor, the cost of integrating it into the rest of the hardware. Same with a multi-core CPU. If we implement multiple cores, we also have to implement different data paths and all the rest of the stuff that you need to support those cores. It's not as simple as saying that if we have another processor or if we have another core. So if we go from 1 to 2, we don't double the speed. It's not quite as simple as that. Fortunately, there is an equation that we can use, and it's called Amdahl's law. You should go look up Gene Amdahl. He was very much involved in creating processors decades ago and thought about an awful lot of these things. And one of the things, as I say, is Amdahl's law here. And it basically tries to understand the difference when you are executing some code between the bits that have to happen one after the other and the bits that can happen at the same time. So if we are manipulating each of those pixels, yes, all those pixel manipulations can happen at the same time. But the bit where you say, you take this pixel and you take this pixel and you take this pixel, that has to happen serially, one after the other. So you can distribute the data, which then it gets run in parallel, but then there's a serial bit as well. The bit to distribute it and then the bit to receive it back in. So we can work out, if we know how much code is serial, if we know how much is parallel, and if we know how many cores we have, we can stick it into Amdahl's law and get an idea of the speed up that we'll get. So here we've got something that's a 3 to 1 of parallel to serial. If we plug those numbers in there, we can see that from 1 to 2 cores doesn't give us double the speed, it gives us 1.6 times the speed if we can run 75% of the code in parallel. So all of these things depend on each other. So it's not just about the hardware, it's about the software as well and how they work together. There's no easy answers with a lot of these things. Not surprisingly, as you would expect, the more that you can do in parallel, the faster the speed up. The more that you have to do serially, one after the other, you don't get as much increase in speed by increasing the hardware. So these are baked into the operating system, and we have a couple of different types of thread actually. We have user threads, so ones where the users create them themselves, and we have kernel threads, ones where the kernel runs multiple protected threads on its own. And you can see there that different operating systems usually support both, including Windows. So there's a library for Windows, for example, called the Windows Threads library. And if you're writing code for Windows, you can use that library to create user threads. Those threads are then executed by the kernel in protected kernel space using its own thread system. Why? Because the kernel knows what's going on. It knows how many threads it can execute at once. There's no point in you as a programmer launching 64 threads if you've got a 2-core CPU. I mean, you can launch them all you want, but you're still not going to run 64 things at once. So the CPU has to take the requests for threads from the user and translate those into what's available on your system. So it will translate user threads to the kernel threads. And as ever with these things, There's multiple ways that that can happen. So the first thing that could happen is we could have lots of user threads, and they are all run by a single kernel thread. And if there's only one kernel thread, then there wasn't an awful lot of point doing this in the first place, because they can't be run in parallel. Sometimes that might just be life. You don't write a program knowing how many CPUs or how many cores there are going to be. So you write the program hoping for the best, and then the operating system gives you its best. And sometimes that best is one processor with one core. So all those threads that you're running just simply go in and the kernel executes them one after the other. So there's nothing actually happening in a sense. The other way of doing it is to have a one-to-one relationship. So every time the user program generates a thread, the kernel maps it to an internal kernel thread, and there's a one-to-one relationship. Now, again, there's some management involved here. So even if there's a one-to-one, you're still restricted to the number of threads that you can run in parallel, and that's dependent on the hardware. There may also be some management going on. So you might have multiple processes running on the system, each of which is generating multiple threads. So in the same way as we manage CPU time with processes, we might need to manage thread time. In fact, we might just say to processes, no, you can only have this many threads because I've got other services that I need to manage, and I need to give them resources as well. Another way of doing it is to have a many-to-many model. Here you simply say, right, okay, I want all these threads, chuck them at the kernel and say, you sort it out. And again, different operating systems will support this in different ways. So as you see that I've mentioned there, Windows has something called a thread fiber package. So if you want the operating system to work this out for you, throw it at the thread fiber package, and then you just create what you want. That way, when your program is run on a different piece of hardware that can scale better, the operating system will go, oh, look, we've got more, and we'll do something here. So the operating system will create the number of threads that it can based on the number of threads that you've asked for. As with pretty much everything we do, there's every sort of combination of those. So everybody that's written an operating system has had to decide how to implement this. Some of them have stuck to the basic ones. Some of them have gone to multiple ways of implementing it. So some have a two-level model where you have a many-to-many and a bound model, so that some threads are bound and some aren't. So you'll find all sorts of different models based on what the designer of the operating system expected to happen with their operating system. So like I said, none of this can happen unless you have support in the code. So there'll be libraries that, and I've already mentioned a couple, to allow you to implement that. So when you're creating your program, you will create threads in your user space, and then the operating system will bind them to the kernel threads that it knows about. Other operating systems take other approaches. There's things called Pthreads. And the idea was to standardize how threads are run. So you can see it's a standard by IEEE. Does IEEE mean anything to anybody? Oh God, he's asked a question and I wasn't listening. IEEE, anybody? No? The Institute of Electrical and Electronic Engineers, or it could be electronic and electrical, but you get the idea. Not surprisingly, a lot of standards for computers are actually bound up into the underlying electronics. So the IEEE standard creates a standard for creating and synchronizing threads. It's called the POSIX standard, which is why it's a Pthread. So it's not an implementation, it's a standard, a spec that says this is how you should do it. And lots of operating systems follow that, particularly Unix-based systems, which, don't forget, includes Macs. So let's look at a couple of examples. For Windows, all the way back to Windows 98, there was a Windows API for threads, and that was a one-to-one process. So one user thread, one kernel thread. And as with processes, it keeps some information on them. So before we had a processor, a process ID, now we've got a thread ID. Before we had a process, set of process data, now we have a register set for the swapping out of the threads in the same way as we would swap out processes, depending on how many threads we can run at a time. There's different stacks, so different data storages for each of the threads, all that kind of stuff. All of this thing taken together, the state of the process, the state of the processor, the memory location, the program counter, all that stuff that you've seen at the low level, the fancy name for that is the context. So the context of that thread is where it is just now and all the data that's set up. So again, we spoke about this last week in the context of the little man computer. If you had to stop that little man computer and load in a different process, you would have to save the program counter to know where you were. You would have to save the contents of the accumulator to know where it was. You'd have to save all that information that's in the CPU, save it to memory, and then load in another process with the same information to start that process running. So that's the same sort of thing happening with threads. And to help the management of it, we might even have multiple types of threads. Thread descriptors. So we have the thread that we set up, it's called the executive thread, and that points to the kernel thread that it's mapped to. Okay, so you have a data structure like that. Our user thread, executive thread, points to a kernel thread, and that kernel thread has a whole set of information around it called the thread environment block with its ID and its data and all that kind of stuff. Linux does the same sort of thing, but it doesn't call them tasks, it doesn't call them threads, it calls them tasks. And much like with processes, if you want to create a new thread, you can use clone and you create a new clone of the parent task. So same idea, just implemented in a slightly different way. And don't worry, you don't need to remember those Linux APIs. It's just to try and give you an idea of how different systems approach it. And you'll be relieved to know that it's a short lecture this week and we are done. Does anyone have any questions?
Well, it's fairly straightforward.
Okay. I'm almost certain I can hear birds tweeting and knotweed rolling down the road at the moment. So I'll assume there's nothing at the moment. Let me just stop the recording.